Hi, everyone. Thank you for your patience. We're still waiting for some panelists, but we don't want to keep you waiting any longer, so we're going to get started. So welcome to Twitter Spaces, everyone, for this episode of Processing Out Loud. And today we'll be discussing liquid supercomputing. I'm your host, Marcus Yam, technology evangelist here at Intel. Today, we're going to talk about the basics of liquid cooling, its advantages, the Lenovo Neptune system, that's going to give you a hint at who our special guest is, and the future of supercomputing for both Intel and Lenovo. We're waiting on one of our guests, but I can introduce our resident expert on this area, Torsten Kuter. He's the Global Account Manager for HPC and AI here at Intel. So, Torsten, thanks for joining me. While we wait on Matthew, I'll give him an intro in a little bit. But could you give yourself a little bit of a self-intro? Tell us a little bit about yourself.
Yeah, thank you, Marcus. My name is Torsten. I'm based out of Germany. I'm part of the global Lenovo account team. I'm in charge of, as Marcus said, the global HPC and AI business with our customer Lenovo and our partner. And we're together driving this business forward.
And how long have you been with Intel?
Well, I'm now 17 years with Intel. I only plan to stay 5. Somehow it got longer.
So what put you in the time warp where 5 became 17?
Well, actually, technology, right? I mean, you have the opportunity to basically change the world with technology, and that's a very interesting topic. I know you're very well aware of liquid cooling in the client space. I've been working on the client space for many years, and I think just back in 2018, I moved into the data center space, which is a completely different animal. And so that's what made me actually staying that long.
Oh, wow. And so you mentioned that you're in Germany. Can you tell me about, is there something specific to your role or the HPC and AI business that you're in that has you based in Germany?
No, actually not. I mean, actually, we as a account team, we're about 70 people. We are really across the globe. We're a very diverse workforce, working from every place on this wonderful planet. So there is no specific reason why I'm based in Germany, while Lenovo is based out of Raleigh and Beijing, basically.
Yes, and I'm here on the west coast of the United States. I've just heard that we have our special guest Matthew Ziegler, Director of HPC and AI Performance Architecture at Lenovo. So, Matthew, so glad that you made it. Would you please give yourself kind of a quick intro?
Yeah, thanks for having me today. I really appreciate it. So, as Marcus said, my name is Matthew Ziegler. I'm a director here at Lenovo and on our high performance computing and artificial intelligence team. I'm primarily responsible for a lot of how we design supercomputers, as well as the performance of those supercomputers, and additionally responsible for the strategy of our overall hardware platform for high performance computing. I'm actually based out of Colorado, but our headquarters are in North Carolina, in Mooresville, and I sit at about 9,000 feet in the mountains and in tons of snow at the moment.
I hope you're a skier.
Yes, in fact, there's a resort about 15 minutes away, which is why I relocated here.
I am super jealous. I'll have to look you up next time in Colorado. I've always wanted to. I've never been to Vail or any of those big resorts, but I would love to know your secret spots some other time. But I'm glad we're talking about snow and cold stuff and winter sports, because you're both here with me today to help us understand how and why liquid cooling has proved revolutionary to help increase the performance of supercomputers. So I'm going to start with some of the basics. So at the most basic level, what is liquid cooling for microprocessors?
So liquid cooling, well, actually, let's take a step back, and I'm sure everybody's familiar with how computers are cooled traditionally with air before we get into liquid. So like you have a laptop, I have a laptop that I use at work, and every so often you might hear the fan kick on. A microprocessor has on top of it what we call a heatsink, and those heat sinks are designed. If you've ever opened a computer, you can actually see they're often copper or aluminum, and they're finned, and it's meant to basically through conduction take the heat away from the processor, send it into the heatsink, and then if you blow air over it, you can exhaust that heat out. Heat is really bad for microprocessors, and so you have to have a way to evacuate that heat. As processor technology goes higher and higher, especially on the power side, there's more heat that's generated. As core counts go up, there's more heat. And one of the ways that we look at it from a thermodynamics point of view in a design is how do you design heat sinks or cold plates that evacuate that heat even faster, because we don't want to damage the microprocessors. We're getting into an era where there's so many cores and so much power on a server level chip that heat sinks just can't do the job anymore. We lose the performance of air. Air is very inefficient at moving heat away from the processor. So we bring in liquid, just like you would with your car, just like your automobile, as you have to fill the radiator with your antifreeze that goes across the engine block and then out to a radiator area where then you can evacuate the heat. It's very similar. We have to use liquid. Liquid is extremely efficient, 25, 30 times more than cold air across a heat sink. And so we're being forced in that direction as technology and drives higher core counts.
So higher core counts are something that we're appreciating too on, as end users, as client PCs. So, I'm kind of showing my level of experience here when everything you talk about liquid cooling, air cooling in my head, as you explain it, I'm thinking about how I'm using these big radiators for, my gaming PC. So from that context, for people who understand air cooling and liquid cooling for gaming PCs or even their own, desktops, since your space is on the HPC side, supercomputer side, what are the differences and unique challenges presented by cooling a supercomputer or a data center that people who, like me, who do gaming PCs don't have to think about?
It's all about scale. So if anybody's ever been into a data center, you're looking at a gaming PC. How do I deal with one? We are talking about dealing with thousands to tens of thousands. And when you start stacking them all together, the amount of heat that gets exhausted, I don't know if you've ever put your hand on a gaming PC, the exhaust that comes out of there, it's pretty hot.
Yeah.
So if you actually now times that by 10,000, the amount of heat that's put inside a room, think of the temperatures that you'll get to. So that's one of the biggest challenges we have is scale, right? So that we can't be heating up your room. And so we've got to we've been leveraging liquid to actually send it outside of a physical building where we can evacuate that heat into the universe, if you will.
Well, and during the wintertime here, I think that would be kind of appreciated. Where normally it'll make the room kind of hot in the summer when I'm running a high intensity workload. But data centers are a little bit different. Now, it seems like I assume that a higher level of intricacy and complexity is needed to cool a data center compared to just my one PC. Is there any cooling technologies that are shared or trickle up or down between data centers and regular client PCs?
It's actually the same kind of approach, if you will. So your client PC has fans. Those fans blow the air out, and then when your fan blows the air out, the room then deals with it, right? So if you're at your house, what happens to the room in your house? It starts getting hot, right? The temperature rises in the house. How do you deal with it? Well, you could probably open a window. In a data center, we don't have windows to open. So we have to have air handling. We have to have exhaust chimneys. You have to deal with that heat. The problem is the heat, if it stays in the data center, that gets sucked back in the front part of the server, and all of a sudden you have higher temperature heat going, basically swirling around, and you just start cooking within the room. So we need air conditioning to feed into the server, colder air, and then you have to exhaust that heat. So that's a data center challenge. When you look at a data center, they have huge air handlers, both to deal with the exhaust and to deal with the ambient temperature of going inside the server. That's a primary difference, is when the room starts heating up, we have to deal with it. So without liquid cooling, your servers are producing heat, but your data centers require energy to run the air handlers, require energy to cool the air, and so that's highly inefficient, and that's why you see in the news a lot of these data centers, and the amount of power that they generate is not so great at the moment.
Got it. And Torsten, I know that Intel kind of plays a big role in this too. What is do you have anything to add to that?
I think if you look at the liquid cooling, the scope of liquid cooling keeps expanding, right? I mean, you're not looking only how to cool CPU or GPU, the memory. Then you look into the PDU, right? So basically, even and then basically what Matt said, it's not only that you have to cool one chassis like with a desktop gaming PC. It is in multiple chassis in one rack, and then basically multiple racks in one data center at the same time, and basically in a constant fashion, and everything together in the same way. That's the challenge.
Okay. I've got like a little outline of questions I have, but I do want to know that to let everyone know that this is an interactive Twitter Spaces chat, of course. So we do have a listener question in. So I'm just gonna, guys, excuse me for the tangent, but I want to make sure people know that we are listening. So we have a question from Atif Attar. He or she asks, if weather simulations had to be carried out, in simple words, what would the process be? How would liquid-cooled supercomputers help in the process? I don't know if the question is about specifically the workload of weather simulations, or whether it is that what you said, Matthew, about hey, the air temperature outside could affect things. So I wonder if you guys knew had an answer, or at least something to touch on about weather simulations.
So I can take that a little bit. It's interesting that you bring up weather. I'm gonna use this as like weather forecasting. It's how I'm gonna kind of approach this. If it's not right, feel free to ask the question again. A lot of the large facilities that are responsible for weather forecasting in the U.S., you think of NOAA. There's the UK Meteorological Office. There's Malaysia Met. Korea, all the countries have these weather forecasting systems, really important for typhoons and things like that. They need highly accurate, they need to be able to process a lot of data that come in, and sometimes in a very quick manner. So as we evolve into higher core counts on the processor, as it generates more heat, we want to be able to continue to go to higher frequencies and more cores to improve the speed and the accuracy of that weather forecast model. So right now, in the last year and a half, almost all of the weather installations or systems that are being installed are all going to liquid. Liquid cooling allows for temperatures. Well, let me rephrase this. Liquid cooling allows for high performance heatsink performance. So it drops the temperature greatly, so you don't get close to a thermal event. If you don't have a thermal event on that microprocessor, you can run the highest frequency at that processor as possible. So the weather forecasting facilities are migrating to liquid to drive every ounce of performance out of that chipset that Intel puts in on their innovation side. And we're seeing accurate models, we're seeing fast models. Sometimes it can be a life or death situation. A good example is forecasting for Antarctica. A lot of the scientists down there, they have to have the weather changes so fast, they're doing multiple models a day and being able to understand if they can even go outside. So the faster they can and the more accurate they can process data is really, really critical. So they're on the bleeding edge of processor technology.
Great. And again, thanks for answering that, and thanks for the listener question. I'll remind everyone, if you have a question, please tweet it to @Intel. Remember to include the hashtag processing out loud. So Matthew, going back to just what you said about the performance, right? Clearly, there's a performance boost that liquid cooling enables, and you talked about air. Is there a way that you could quantify just the extra performance boost that liquid cooling enables, and perhaps maybe even put into context that you said that there are meteorologists that are running these simulations? Would you say that would if we didn't have the technology available for liquid cooling, would this mean less accurate forecasts or not being able to run so many simulations? What does that truly enable? Liquid cooling, that is.
Right. So anybody, especially during hurricane season, what you often see on TV is newscasters. They're looking at weather model, and they're constantly updating. So it's really important. So if you have a slow computer that takes a long time to crunch all of the pressure data, all the input data to figure out the path of a hurricane, think of what happens once that hurricane is on a city or a town and they couldn't get the information fast enough to evacuate. So it's really critical to not only be fast, but to be accurate, to understand directions of weather patterns, if you will. When you asked at the beginning, the benefits of liquid cooling, if you go look at a processor and let's say you're out there Googling it and you say, I want to know what this processor can do. Oftentimes it gives you a base frequency, and then it gives you a turbo frequency, and Intel give you an AVX512 frequency. They're all over the map. A lot of this control is based on the thermal capabilities of that processor. And what I mean by that is each processor has a limit that if it gets to that higher limit and it gets too hot, if you will, it has protection mechanisms built inside it. And the first one it does is it will throttle frequency. And so your processor might be at 2.3 gigahertz per core. And if you look at it, it might be running at 1.8. The lower the frequency, it decreases the amount of heat generated. So in air cooling, you often see these throttling events if your system gets too hot and your fans can't blow enough air over it. So the processor takes a safety mechanism into its own hands and says, hey, I'm getting too hot. I'm going to kind of shut down here. With liquid, we can stay so far below that threshold for throttling that you can continue to run at the highest frequency possible. So if you look at that spec sheet and it says the turbo frequency is 3.1, you actually can run at that 100% of the time for the most part if you're running liquid through it at nominal temperatures. So that's another benefit of liquid cooling, is that performance aspect.
It's really interesting to hear that you talk about, like thermal throttling, because these are things that, at least in my background as a PC gamer, that we think about as well. Of course, it's on a much larger scale, but we do pay attention to, our cooling, because we want to sustain those turbo frequencies for as long as possible, even more so on the notebook space. So it's pretty interesting to hear that, hey, this stuff kind of behaves similarly, just at a much higher level. With that in mind, given that when I look at, we're talking about scale, right? Not only in terms of scale and how many processors, but exascale computing. And we were just talking about weather, right? So I want to talk about the impact that our computers have, data centers have, on both power consumption and on the flip side, sustainability. So what are the impacts that liquid cooled HPC systems have on the, I guess, power consumption and sustainability, and the ramifications of these considerations?
I mean,
yeah, go ahead, Torsten.
Yeah, I mean, consider that the data center consumes 50x the power than the laptops around the world, right? And this power demand is increasing 12% on average every year, and we're through years to a pandemic, and we all probably have been using things, even if it's a high performance computing, but we have been using data centers much more intensively, right? So, and with liquid cooling, you can have a severe impact on that power consumption, and basically you can, on a data center level, and might have more numbers than I, maybe up to 40% reduce that number, right? Which is huge. You can, even with small things, because liquid cooling is not just one technology, it's different parts of technology. You can go from single percentages to large double-digit percentages. So liquid cooling really can make a difference, also in regards to sustainability.
And actually, if you think of scale from a power point of view, when I'm talking about air cooling, what do you need to get air cooling? You need to have a fan, right? You need to have some mechanical device that can move air from one area to another, and that's fans. And they're in laptops, they're in gaming PCs, they're in servers that are air cooled. As we start increasing the power, the amount of power that a fan needs goes up exponentially. Actually, it's a cubic factor, the amount of power input. So now for one laptop, okay, maybe it takes 10, 15 watts of power to run the fan. Not very big on a grand scale kind of thing. But if I have 150 watts per server and I have 10,000 servers, think of all of that power you need just to run fans, right? You're not doing any computing, you're just moving air. So one of the sustainability things around liquid is, what if I took the fans out and I don't have the fans and I use it and I use 50 watt pump instead to run, instead of tens of kilowatts for fan power. That's a better, that's a smaller carbon footprint for a large data center like an Amazon's or a Google's, or these large exascale customers. It's critical for us to think that every bit of electricity that goes in should be doing work for computing. not work for generating cold water or work for generating air movement. Does that make sense?
Yeah, in
Take away the
fact,
fans and you save a lot of power.
and you mentioned something else as well. Is that talking about cold water, that sort of thing? You made me just think of that. I've read about some very large data centers are specifically strategically located in specific parts of the world where the local geography allows for access to, I don't know if it's cold air, cold water, maybe even using hydroelectricity. How common is this that you would place a data center somewhere in the world to take advantage of where it's at and the local climate?
Very advantageous. So Iceland actually is a great place for people to put their data centers. There's a lot of European entities that are locating in Iceland, and because they have geothermal, and that's a way of generating power to go into a data center. So when we're talking about location, it's not necessarily a cooling benefit, although you do get that. I always envision just opening the doors to the data center in Iceland. You get great cooling in that way, but mostly it's around geothermal. It's around generating the electricity that goes into the data center. So if you're using renewables, Google's put some on river areas so they can generate hydroelectric power that goes into it. So it's a, we're talking about cooling the servers, but if you actually take a step back and think about the whole ecosystem of what a data center can do, anytime you can draw power from a renewable, your carbon footprint goes to zero, or can even do negative if you're reusing some of that energy that comes out of it in the form of liquid heat in the liquid.
And Torsten, I'm sure I see you got something to add to this too.
Yeah, there's a good example. Take Harvard University. The data center is directly next to a river, but not for the reason of the cold water to keep to cool the CPUs, the racks, whatever, because that's actually warm water cooling, not cold water cooling. You wouldn't put cold water on a hot CPU, right? But basically, there is meant to generate energy through the hydro plant. So they're using green energy to run the data center, and then liquid cooling to cool the data center. But it's then warm water cooling.
That makes sense. It seems that the design philosophy that we have around semiconductors, around efficiency and performance, translates over to the bigger system, both not just inside the chip, but everywhere outside too. You've both given me really good basics on liquid cooling and why we do it and the benefits. But Matthew, since we have you here today, I do want to talk about Lenovo and the Lenovo's Neptune system of liquid cooling. So could you give me like an overview of what is Lenovo Neptune?
Yeah, so we've been doing liquid cooling for over a decade, and when we started doing liquid cooling, the whole reason to get into it was around efficiencies and power savings. Going back to that point, I said if you can remove the fans, you can save power. So we started working with some European customers that were paying really high kilowatt per hour cost, and the whole goal was to generate basically to lower the cost of operation of a data center, of a supercomputer. So we worked with large university out of Munich, where we put in 10,000 of these systems, and there were no fans, and then there was a lot of calculation around how much savings in power did they have on their power bill, if you will. Then all of a sudden we did this transition a couple years ago around an efficient story to a performance story. So working with Intel, are masters at chip innovation, instruction sets they put in, how they do transistor design and stuff like that. And the more they packed it, they scratching their heads going, man, we're getting to the point we can't cool this with air. Let's work with Lenovo. So we started teaming around how we would do the thermal piece of it as you guys drove the innovation on the chipset. So we would work hand in glove, being able to kind of put these in the market and make sure that they didn't overheat. So as we were doing this, we were talking to customers, and we were like, immediately get in the weeds of thermodynamics and physics. And it was really hard for customers to understand, overall what is liquid, what it does, it doesn't do. And we sat as a team and said, liquid's expanding. The way you can do cooling, you can do direct to chip, you can do what we call liquid to air heat exchanging. There's just different approaches to use liquid to remove heat from a system. And we here at Lenovo came up with the Neptune sub-brand. Neptune is the way we, kind of threw out names. The one that won was from one of our new hires that just walked into a room and said, "What about Neptune?" And it was like, man, how can you actually, we've been spending a month on trying to figure out how to brand this thing, and he did it in 2 seconds. He didn't know the power that he wielded, I guess. But we came up with Neptune because I believe it's the Roman god of the ocean. I could be wrong there, but it's one of the ocean. It's either Greek or Roman, and he has a trident. And at the time, we had 3 different approaches. We had a kind of a phase change where you use liquid in a method that it would evaporate, and that's how you would be able to remove heat when it touched the hot chip. It would evaporate into a vapor. So that was one way to use liquid. Another way, we were doing rear door heat exchangers that was helping to remove heat out of before it got into a data center. And we do direct node, which we call direct water cooling, which uses liquid through cold plates and pipes to remove heat from anything that generates heat. So the Trident, the 3 products, and the branding, now when we go out, anything that's liquid cooling at Lenovo falls under our Neptune brand.
Well, not a pun, but very, very cool, or pardon the pun. I'm going to tie in a listener question right now from Kevin Bonington. I've actually seen some of his builds that he shared on social media. He's a avid PC builder, and he loves to make very cool looking gaming PCs. And he asked the question, and I'll kind of tie together with mine. Can you give me a kind of a visual description of what liquid cooling looks like from Lenovo Neptune compared to someone who's only had that context of an all-in-one PC, because you have your one big cooler that goes on your CPU and then goes to a radiator, and it's just like it's a one-to-one system. With these large data centers, do you have a radiator for every single processor, or do you have like a gigantic fan, a gigantic radiator that's on the top of your building? What does Neptune look like?
So it's actually the latter. So outside the building, we want to get heat out of the data center. So that's the first visual you want to have, is think of a big radiator on top of a building. Okay. Now, how do you get the liquid to the radiator? What we do is we have what's called a cooling distribution unit. It's a pump that regulates pressure and temperature of the liquid going in and out of the system, if you will. And these servers don't have radiators inside them. They actually have a whole loop, very much like hoses, if you will. We use copper, so it's a fixed loop. So think of like plumbing. And there's hoses that attach to manifolds in the back, and the manifold is responsible for taking that water in and out of various servers. So it goes in. The water will go in. It will go across the CPUs on a cold plate. It actually is a plate that has fins inside it, so the liquid fills the plate. You're not touching the microprocessor with liquid. It's actually there's a barrier, if you will, a metal barrier, and the liquid is sitting on the inside of that barrier, and the other side is touching the microprocessor. Very much like you see in a car engine. It goes across everything that generates heat, then it goes out of the rack, and the rack is about the size of a refrigerator, if you will, and it goes into the cooling distribution unit, and then there's a transfer of heat to another water loop. That water loop then goes to that radiator on top of the building, and that we say evacuate into the universe, if you will. So we get it out of the data center. We don't want heat exchange inside the data center, or else you have to have another method to get it out of the building.
And these are very complex systems. I know that it really takes 2 companies like Intel and Lenovo to work together to really bring these together. So just rounding out our last batch of questions in our final handful of minutes, I have a question for both of you. I want to hear from both Torsten and you, Matthew. How would you describe kind of the partnership between Intel and Lenovo developing these liquid-cooled supercomputing systems? And if there's another thing if you can add on, I want to hear if there's some engineering challenges that the 2 companies had to come together to solve. Torsten, why don't you start? Torsten, I think you might be on mute.
I think the collaboration started a decade ago, as Matt stated, right? I think the first technology, liquid cooling technology, was about 2012. Since then, we're really co-developing those solutions, and if you think about just in 10 years that the thermal design point for CPUs grew more than 2.5x, for GPUs the same, and memory 4x, you can envision that the time and resource you need to invest to always develop more efficient cooling technologies is incredible. I mean, talking about the future, I mean, right now we're discussing not the next generation, but the generation after the next one, and how we have to completely redesign the server racks ground up with different orientation of the nodes. And that's a really interesting topic, right? So it's not like simple plumbing and piping. It is really to optimize the liquid flow, increase the pressure, because I mean the kilowatt per rack increased over the last, yeah, let's say 7-8 years, from 66 kilowatt per rack to next generation maybe 180, and the next one even more. So you can see that really requires smart engineers and smart solutions in order to come up with ever better cooling technologies.
And Torsten, we've talked a lot about just how the liquid cooling works from a physical perspective, and how we've had to build some of this stuff from the ground up. But what are the benefits? What are our customers getting? What is the rest of the world getting? I know we touched on weather simulation, but what problems are these systems solving really in the real world?
I mean, that's really going across different workloads. I mean, from seismic over medical research, climate research, astrophysics. These really complex challenges of humanity. Those things are running on those high performance computers, and that's what's for me make me wake up every morning and drive even further.
Yeah, here at Lenovo, our kind of our motto from our HPC team is solving humanity's greatest challenges. And one of the one that's pretty relevant, I think, to everybody here is around COVID. When the COVID virus was first discovered, we were able to use supercomputers to basically not only sequence the genome, but learn about how the proteins folded on itself in record time. Once we knew how the proteins looked, we could target therapeutics and vaccines to it. That's one of the ways you saw such fast development in the medical community around COVID therapeutics and vaccines, was because of supercomputing. Once they understood the three-dimensional structure of the virus and the proteins and the active site within it, you go right into drug discovery. Drug discovery is sped up through high-performance computing also, because you can eliminate candidates pretty quick. And so all of that uses supercomputing. It's so solving humanity's greatest challenges, whether it be oil extraction to medical research to sending rockets into space, it's all using supercomputing. And actually to movies. One of our liquid cooled customers is DreamWorks. They use liquid cooling to facilitate the speed up of their rendering capabilities. So it's all over the place.
Wow. Well, you've increasingly piqued my curiosity. I feel that this could be a multi-part series, but we're actually running out of time for today. So I guess, like this, all good things must come to an end. Hopefully we can revisit it. And I'd like to thank you, Matthew Ziegler from Lenovo, for joining me, as well as my colleague Torsten Kuter from Intel for joining me. I'm Marcus EM. We look forward to having you join us all next time here on Twitter Spaces for the next installment of Processing Out Loud. Again, thanks to our guests, and thank you everyone for tuning in. Stay safe out there. I'll see you next time.